Thanks, Margaret, and for all of you for being here. This talk follows really nicely from what Hava just shared. This is a collaborative effort involving many folks in CALS and in the Extension Ag Water program. And so really our goal is to begin a science assessment assessing the effectiveness of different best management practices to decrease phosphorus losses to water. And this is really being done in the context of Wisconsin's nutrient loss reduction strategy. And so if you're not familiar with this and you want to learn more, feel free to check out this QR code. I'll show this again at the end of the talk. But really the goal of this is to be descriptive and sort of game out the relative benefits and sort of costs of different potential strategies to deal with phosphorus across our diverse cropping systems in Wisconsin. The goal isn't to prescribe any particular strategy to the ag community, but sort of to look at the solution space. And so as I mentioned on the last slide, we have a number of scientists involved with this process and soliciting input from the stakeholder community. So we're fortunate to be able to really build on the efforts of other states in our region that have already begun doing these sorts of science assessments. So back over a decade ago, the EPA asked states in the Mississippi River Basin to formulate nutrient loss reduction strategies to deal with nitrogen and phosphorus loads to the Gulf. As part of this, many of the states conducted science assessments to begin evaluating different scenarios to actually address those goals. And I'll pick on Iowa, since I was a faculty member there for a number of years. And they were one of the first states to actually do this, to begin to synthesize the scientific literature on nutrient loss practices. Their report came out in 2012, and they've been updating it ever since. And I think it's a really sort of a useful point of departure to think about what we might be able to do to add and sort of complement this work. And so one of the key findings of their reports are these tables that list practices and list sort of the typical reduction in nutrient loads that we might expect from those practices. So I'll walk you through this kind of dense table. And so this red box here shows you the average phosphorus load reduction for a number of different practices of interest. So there's a value, and then there's a standard deviation in parentheses. And what you'll note is that for many of these practices, the variability is a lot higher than the mean, right? And so this is challenging from a public policy perspective if we're trying to think about, well, what practices are optimal, right? And if we zoom in on one practice in particular, right, using a winter rye cover crop, great, we know there's a lot of environmental benefits to be had from growing cover crops. But when we look at phosphorus in particular, right, average load reduction of 29%, plus or minus 37%, potentially wild swings in either direction, this really begs the point, well, where are there specific places that we should prioritize for using cover crops? Can we actually dive into this variability and predict it, right? And what's going on here? I think a lot of people might be hesitant to allocate cost share dollars to a practice with this level of variability. And so I think it really merits consideration of what data sets are used to actually calculate these values. And so what my colleagues in Iowa did when they were putting these together is they were drawing on peer-reviewed studies from across the Midwest, including a number of studies from Wisconsin. And these are studies that had to have explicit treatments and controls that were replicated. Right, this is really important because Hava just showed you some great work that relied on these paired watersheds, right, allowing us to assess water quality benefits at field scale. Those studies are not included in these reports. I think it's a really important philosophical decision that was made. And so the consequence is that we're left with very little data to actually inform these tables. And so when we look at this winter rye cover crop example, there's actually only 6 site years of data going into this number, which is then being extrapolated, in this case, across the entire state to sort of guide nutrient loss reduction efforts, right? So I think we can do better. And so, just sort of, this is the 2012 report, right? This is now being updated. So I have early access to this. Now we're up to 12 site years, right? So we're sort of relying on random acts of science to actually bolster this database over time. And I think we're not able to make the kind of progress we would like to. So right, we're at the Dairy Innovation Hub, got to talk about manure, right? One of the other practices of interest is whether, in parts of the landscape that have been relying on commercial phosphorus fertilizer, if we replace this with manure, can we get some water quality benefits? Well, maybe, right? The devil's really in the details. Some encouraging trends towards reduction, but again, really wide error bars, right? And so I think we're going to need more than just these plot scale studies to make progress on the issue. And so, right, folks that have taken experimental design, this is really the fundamental challenge. If we want to evaluate these practices with replicated studies at the field scale, we're going to have to make some plots, we're going to have to randomly assign them to treatments and controls, and figure out a robust way to actually measure nutrient losses from these plots. But of course, right, we all know this is superimposed across our variable fields and landscapes and watersheds, right? And particularly for phosphorus, it's that transport and delivery from up in the watershed down to the edge of the basin that becomes really important. So arguably, right, these paired watershed studies are a better way to address the problem than these replicated plot scale studies. And so, well, how do we make progress? Well, I think there's a couple of ways that our team has thought we might be able to do this, right? The first is relying on the phosphorus index, which Hava just shared, right? This is a nice model that's been rigorously calibrated with Wisconsin data that allows us to game out the context dependency of these different kinds of scenarios. And then we've also got a wealth of sort of raw data that have gone into actually helping to calibrate and validate that phosphorus index. So for almost 25 years, folks have been monitoring the edges of agricultural fields in the Discovery Farms program, and there's a lot of ways we can leverage that data to greater extent to evaluate some of these practices. Okay. So again, I don't have to belabor this. You just saw a great introduction from Hava on the P index. But again, just to emphasize, right, this is a semi-mechanistic model where we're actually using physically based mechanisms to look at erosion and runoff, et cetera, and actually transport of these relevant phosphorus fractions, taking into account, the really important soil characteristics and the crop management attributes of our systems, really. And the key point, again, is that this model, I think, does strikingly well when we drive it with real weather and runoff data. And despite the fact over longer timescales, right, we're not going to be able to get the exact data we need everywhere, but the key point is that we can actually rank fields in order of their risk of phosphorus loss according to these practices. And so that's really sort of the philosophy that we're gonna run with for this effort. Okay, and of course the model continues to get better over time as we get more data and are able to include more of a mechanistic representation. Okay, so what we're going to do, right, we're going to try to broaden this solution space to look at the context and its impact on our nutrient loss reduction practices, right? The same practice that works, at the bottom of a hill slope in a poorly drained soil is not necessarily going to be the same practice that we want to think for our highly erodible, more vulnerable soils, ditto for our different kinds of cropping systems, right? All of the various flavors of dairy management that we have in Wisconsin, all of our grain crop systems, et cetera. And so what we're going to do is look across our state. We're going to stratify our analyses by the different agricultural statistical districts across our state, which really sort of highlight these differences in soils, weather, management practice, et cetera. And when we do this is a great map that Hava generated a few weeks ago, right? These are all of our agricultural soils in Wisconsin. There is a lot of yellow pixels there. But importantly, they differ in really key ways in terms of their fundamental physical properties. And so we're using this sort of as a baseline against where we're going to manipulate all of these other agronomic and conservation practices. So looking at how differences in soil test phosphorus, crop rotations, use of cover crops, various tillage practices, differences in nutrient source rate and timing, edge of field practices like vegetative buffers. And so we're in the point where we can then begin to calculate these thousands of scenarios in SNAP Plus using some developments in a batch tool that's really close to being used. So just to highlight an example here. And so what we're going to do in each one of these agricultural statistical regions, we are going to call out the dominant soil series that are likely to be most representative, as well as some of the most vulnerable soil series where we can potentially have biggest bang for our buck when we're thinking about conservation practices. And one of the exciting messages that has emerged is for many of these regions, we can capture a good chunk of the area of agricultural land with relatively few soil series. So this example is from north central Wisconsin, where we can get about half of the ag area in terms of these three silt loams, the Loyal, the Withy, and the Magner, right? And so that begins, to give us a sort of a representative template of soils for the region. In addition, to these potentially vulnerable soils, right, more erosion risk that are on much less of the landscape, but again, potential for disproportionate water quality benefits if we might target these soils for management practices. Okay, and so, perfect, 5 minutes. All right, so just like to highlight an example here of this context dependency. These are some previous analyses from Laura Good. This is really looking at how, the benefits of changes in tillage practices really differ depending on the kinds of soils that we're considering. And so this is a site in northeastern Wisconsin, so sort of a typical corn and soybean rotation that receives some fall liquid manure. Typical soil test phosphorus values. And there are three dominant soil series in this system. There's this Hochheim soil. There we go. So, and these are plotted with their p-index values. And you see really this Hochheim series has the highest p-index. Well, that's really because of its landscape position in part, right? These are steeper slopes. The soil is more vulnerable to erosion. This purple bar is the particulate phosphorus index, and the kind of lighter blue is the soluble phosphorus index. You can see that two neighboring soils have much lower phosphorus indices on average, but slightly higher component in the soluble P fraction. Okay, so this is our baseline case where we're using a fall chisel plow and to incorporate that manure that we're applying. So we can compare this with a no-till system, right? And so there's some really interesting changes that vary as a function of those soil series. So in our Hochheim series, right, with our highest p-index, we're able to drop that by quite a substantial amount by reducing that particulate phosphorus loss. But you'll notice that light blue bar has actually increased, right? By leaving that manure on the surface, this is more vulnerable to loss during winter and spring. Okay, this makes sense, but in this particular case, the loss in particulate P is really the dominant driver in the system and what we want to think about. In our two other soil series here, the Ashcombe and the Pella, right, not much of a change at all. We've essentially swapped phosphorus forms. So by decreasing erosion with this no-till practice, we're able to decrease greatly the particulate phosphorus loss, but we've swapped that with an increase in the soluble phosphorus, right? And this is a really important example, right, about how not, one size doesn't necessarily fit all, right? We can think about prioritizing parts of our landscape for adoption of specific practices. And I think, again, just with this example, this begins to illustrate, drivers of some of this variability that we see in the Iowa report, right? We can't think about no-tillage or cover crops in a uniform effect everywhere. We really have to think about the context. Okay, and so I'm not going to get into this. I was too ambitious, but again, just suffice it to say there's a lot more that we can do with the raw edge-of-field data and sort of the wealth of data that have been collected over the past couple of decades. That's going to be another important part of this science assessment. Okay, let's skip over this. And again, at the end of the day, really the goal is to sort of game out different practices and begin to provide preliminary guidance to start the conversation about what kinds of practices may be more or less appropriate in different kinds of scenarios throughout the state. And really, the goal is to continue this work into the future, right? The first efforts are on phosphorus. We're hoping to continue into nitrogen, which, is its own story. Okay, so Again, our team is really open to feedback and input. This is a relatively new process. Feel free to contact me. And again, if you're sort of curious about the broader context, feel free to check out that QR code. And I'd like to really thank our colleagues at DNR for providing some of the partial funding to jumpstart this effort. I see Carl in the audience here. And so it's been a great experience working with them so far. So I don't know if there's time for questions, or maybe we're moving into discussion now.
Thank you.
Yeah, thanks.